Welcome to AP Chemistry. That's Julia.
That's Charlotte.
And that's Elena. Congratulations on getting approved for AP Chemistry.
You sizzle, kind of like a reaction.
We're going to be teaching you about extended stoichiometry. Get ready
And get excited. Woo!
Just technical difficulties. One second.
Now we're going to be talking about molecular and empirical formulas.
Today we have flowers.
We have 8 lavender flowers
4 white flowers
And 2 pink flowers.
The molecular formula would be L8W4P2.
Say, what's an empirical formula then?
Do you know, Elena?
Yeah, an empirical formula is a formula where the subscripts are at their lowest possible factors while still being proportional to the molecular formula. So what do you guys think would be the empirical formula of this?
Would it be
L4?
W2P?
Great job, you guys!
Oh my gosh!
Yes! Wow, so now we learned molecular and empirical formulas.
Wow.
Let's show you with a real problem.
Hi, my name is Professor Emmel. Today I will be teaching you about empirical and molecular formulas. The question we will be answering today is, caffeine has the following percent composition: carbon 49.48%, hydrogen 5.19%, oxygen 16.48%, and nitrogen 28.85%. What is the molecular and empirical formula? I'll show you how to do it on the next board. First, write down what you know. Got it? Great. Next, a good trick is to assume the sample is 100 grams and put all the percentages into grams. Awesome. Let's start with carbon. Take the grams of carbon you have found and divide it by the molar mass of carbon, which can be found on the periodic table. This tells you approximately how many atoms of carbon are in this molecule. The answer is 4.12, which is approximately 4 carbon atoms. Great! Now why don't you try the rest of them? Good job! It is found that there are 4 carbon atoms, 5 hydrogen atoms, 2 nitrogen atoms, and 1 oxygen atom in the molecule of caffeine. Here is the molecular formula: C4H5N2O. An empirical formula is the molecular formula where the subscripts are in their lowest factors, but are still proportional to the molecular formula. Because each of the subscripts in this molecular formula are already at their lowest factors, the molecular formula of caffeine is also the empirical formula.
Hi! This is percent composition. We're going to show you it through granola bars.
I have a Special K granola bar.
I have Kind. And I have Kashi. Together we make a molecule. How much of this molecule is comprised of Kashi granola bars?
50? 50%?
Yeah, 50.
How much is Kind?
25?
Yeah!
And how much is Special K?
25! That's crazy!
Let's show you with a real example of percent composition.
Take it away!
Hello, my name is Professor Percom, and I'm going to teach you about percent composition. Look here at this glass of water. Ever wonder what percentage of your water is oxygen? Let's find out. First, let's find our molar mass of water. It is found to be 18.0158 grams per mole. Great! Next, we can find the mass of one oxygen atom from the periodic table, 16 grams. Finally, how do we find percent composition? We divide the mass of one oxygen atom by the total mass of the water molecule and multiply by 100 to find a percentage. It is found to be approximately 89%. 89% of your water is oxygen. Gee whiz!
Now let's talk about limiting reactants.
Here we have 20 graham crackers,
12 pieces of chocolate.
And 2 marshmallows.
For 1 s'more, you need 2 graham crackers.
3 pieces of chocolate.
And 1 marshmallow.
How many s'mores do you think we can make with this amount of material?
I think we can only make 2.
Why is that?
Because we only have 2 marshmallows, and if we need a marshmallow per s'more,
We can only make 2 s'mores. You're right. That means we have an excess of graham crackers and chocolate. And what would our limiting reactant be?
The marshmallows.
Yeah. Awesome. Now let's show it with a problem.
All right, take it away.
Howdy, I'm Professor Limry, and I get to teach you about limiting reactants. The limiting reactant is the reactant that creates the least product, because the reaction can only go so far as its limiting reactant allows. Our question is, when 60.0 grams of FeCl3 reacts with 35.0 grams of H2S, what is the limiting reactant? First, you want to write your reaction and balance it. Swagtastic! Then you want to find the molar mass of FeCl3 and use it to calculate the number of moles of FeCl3 in your 60 grams. Got it? The number of moles is found to be 0.4 moles. Using the mole ratio, convert the number of moles of FeCl3 to moles of Fe2S3, which turns out to be 0.2 moles. Amazing work! Do the same conversion for H2S to Fe2S3, which is found to be 0.33 moles. The number of moles from FeCl3 to Fe2S3 is smaller than the number of moles of H2S to Fe2S3, which means that FeCl3 is the limiting reactant. You guys did great.
That was extended stoichiometry.
Hope you had fun!
Because I know we did.
Is it going?
Yes.
Here's why we didn't get in the canoe today.
Ants. Ants. Us and ants. Us here, ants there.
Too many. Just too many. Too many.